Why wouldn't you just give $1 million to each American, I wonder? All right, so let's go. Okay, so we are today looking at exponential growth and exponential decay. We're gonna be taking a look at both of those in this unit. Today we're particularly looking at growth. It's a little more intuitive. Let's go. Here's an interesting thing that might happen if you were breeding dogs. You have these like three female dogs that are your prized like possessions, or they're your prized animals at your dog breeding factory, and they have multiple offspring each, but every generation you keep the best two females, the best two daughters of each dog. Okay, so in generation 1, each dog is going to have another dog here, so we get 6. 6 from 3. Okay. What are we going to get in the next generation? How many dogs? Just how'd you do that? Did you draw each of the dogs? You're a fast artist, speed artist. Okay, I'm not going to do that. I'm just going to say, as you said, 12. So how did you get that number? Just multiply by 2. Okay, cool. All right. So here's what I'm noticing. We started with 3 dogs. And then we multiplied by 2. And then you were going to just multiply by 2 here. And I suspect you'd have 1 dog for each hour of the day in the 3rd generation. Is that right? Is about right? Is about what you're seeing?
Yes.
Okay, all right. And then you'd have like a full 2 days of dogs the next day. So, or the next generation, that is. 48 dogs. Oh my goodness. How many in the next generation?
4 days.
96. Cool. And then after that?
192.
Very good. So there we go. And if we graphed this, if you had a graph, so just make a little sketch here. We've got space there to make a little sketch. This is generations. And this is number of dogs. All right. So we need like up to about 200 there. So put your 200 at the top of your sketch. Put 100 in the middle. Okay. And then we're going to need something like around 50. And then something around 25, and we've got a pretty good scale there. See how I did that? So I created a pretty nice scale just by dividing 200 a few times. Cool, eh? And then we're going to put our generations on. So we got 0 generations there. We want up to 6, so go like 6, and then you put in 3 in the middle, and then you're going to have to divide this in thirds. 1, 2, 3, 4, 5. Pretty cool, eh? Now put your points on. At 0, you got 3 dogs. Barely is over the line, right? After 1, you got 6. It hardly moves. After 2 generations, you're halfway to 25. Still hardly moving. After 3 generations, you're at 25. 4 generations, you're at nearly 50. 5 generations, nearly 100. 6 generations. Whee! Look at that shape. Does that shape remind you of any marble slides that we might have seen recently? Is this quadratic? Because it's curving. It's not a straight line like linear things. Is this quadratic?
It's an exponential function.
Oh, that's so great. I'm so glad I got out of bed this morning. That's so awesome. Yes, this is not quadratic. This is exponential. Now, can we write the number of dogs as some kind of power? Like, can we write this in some form? And I'll give you a hint. If we were to make this a function, it would be in the form y equals some number multiplied by some number raised to the power x. So what would I have for my a and my b if I wanted to write these as a power?
Could you do like A3, B2, and X0?
We should have like half attendance each day because the awesome ideas coming out of you are great. Yes. So take a look at this. We need to take the number 3 and multiply it by exactly 0 2's in this one. So it would be 2 to the 0. Down here, we do 3 times 2 to the 1. Here we do 3 times 2 times 2. That's how Wilson did that. He just multiplied it by another 2. And then you would just do 3 times 2 times 2, and then you would take that number and multiply it by another 2 to get 24. And keep going. That's awesome. That's beautiful. So the whole thing, describe how you determine the number of dogs in each generation. Well, I would put in some sentence like this. I take the number 3 initial number of dogs and multiply it by 2 for each generation of dogs. Makes sense, right?
Yeah.
Yeah, that's about right. Yeah, cool. All right. So, the order of operations performed on 3 dogs to arrive at the number of dogs in generation 6. So, what will my order of ops, my bedmas, look like at this level here?
Wait, what?
What are the operations you do to 3 dogs? And I don't mean like in a practical sense, I mean in a mathematical sense. To arrive at the number of dogs 196 in generation 6. What do you do to the number 3 to get it to balloon up to 196? Jude.
Is it times 2 to the power of 6?
Yeah, sure. Yeah. I take 3 and multiply it by 2 6 times, but you multiply it by 2 to the power 6. We are the same. Yeah. It's good. Yeah. That's good. So it's 3 multiplied by 2 to the 6. So let's go back and can you develop an equation that relates the number of dogs to the generation number? So x equals generation number. All right. You want these types of statements in your word problems because it organizes your own thinking and it clarifies your own communication. It's for your audience and it's for you. So make these type of statements, get in this habit. Your hand will not fall off. Let y equal the number of dogs in that generation. So y is a function of x, but what's y equal to? What's the number of dogs equal to? How do we wield the numbers 3 and 2? With this value x, which represents the generation number. This was for the 6th generation. We had y equals 3 multiplied by 2 to the 6th. That's what Jude said. So how will we use that for the general formula up here? There's the generation number. So what's my general formula look like? I take the initial number of dogs. I multiply by 2 for each generation. Yeah, so that's what our formula looks like. That's what our equation is going to look like in this case. Any of you on Facebook? That's how you can tell how old this package is. We've got Facebook Friend Frenzy. And look at the computers. Oh man, they look like the computers in our library. Okay, suppose you decide to have a party. And we're going to send Facebook messages to our 3 best friends to invite them to the party. Every day, if you receive this invite, it goes viral, and you are like compelled to perfectly send it on to 3 people. So we're going to track how quickly this invite is going to balloon up to the size of the school. Do you know about how many students we have here?
1,552 or something.
That's a better number than I was going to give you. Yeah, I was going to say a little under 1,600. Great. So, how many invites will there be on day 2 going out?
9.
9. Good. Yeah, we got 3 there, 3 there, and 3 there. Every time it's multiplying by 3. So we go 9. How about day 3?
27.
Yeah. So we got, again, 3 there, 3 there, 3 there, and so on, ... Okay, next one. Is 27 times 3 hard?
81?
Yeah, it is 81. Did you do that in your head or on a calculator or?
In my head.
That's fantastic. Here's here's 3 to the 4. 3 times 3 times 3, that's 27. Times another 3. You want to see how to make it easy? Just do this. 3 times 3 times 3 times 3. Because you already know 9 times 9, right? And there's your exponent laws. 3 squared is multiply the exponents 3 to the 4. But that could have been 9 squared. 9 is 3 squared. 9 squared equals 3 to the 4. Equals 81. Okay, let's riff on something else for a little while. 81 times 3. Beautiful. Okay, so here we could write this as like how are you determining the number of messages in each round? Like, what are you doing? Just to that number, yeah?
Just taking your number and changing it by 3.
We just multiply by another 3 each time. That's good. Yeah. So what did we do to one message? We started with one message, so there we go. We start with one messages to arrive at the number of messages in round 5. Round 5 equaled 243 messages. How do we get there? Wait, was that round 5? Yeah, day 0, right. So they're numbering them here. Interestingly, we start at day 0. One invite go out. We could have started at day 1, but then we have to adjust the exponent. This is more elegant, simpler. Yeah. How do we get there to round 5? If we were looking for let's jump here. I think people are ready to jump here. Y equals where you got these statements. Let x equal the number of days. Let y equal the number of invites on that day. Okay? So what would our formula look like? Let's see if we can see some patterns in the last formula we developed, because I felt like we did some good work there. Okay, so I'm going to just write I'm going to annotate this formula up here. I would annotate it as well if I were you. Okay? Here we have 3. Initial number of dogs. And 2 is how much it grows by each generation, the factor by which it grows by each generation. So we're going to label those types of things as yeah, Jude?
So I was saying, for the equation then, would it be 1 times 3 to x?
Yeah. Good. So we're going to call these the growth factor. In other words, meaning the number we multiply by. Okay? Growth factor, a little new vocabulary for us. And then initial value is something that we see with a lot of functions. We see that initial value showing up here in the a value. Now, one other thing that we could look at, take a look. I was just marveling that they have generation 0 there. So that would be like, if we put that in as x, it would be y is equal to 3 multiplied by 2 to the 0. Wait, won't that give us a 0 dogs? Because 2 to the 0 is a 0. It's 1. You're right. I made a mistake. Yeah. No, things to the 0 are 1. You see why it works here in the function? For the 0 time, or when x is equal to 0, the function is just outputting a. It says take a and multiply it by 1. Whatever your growth factor is, your growth factor to the power 0 is 1. So we have down here, thank you, Jude, this is 1 message on the first day multiplied by 3 to the x. Or we could just have the function y equals 3 to the x. It is the same thing. You multiply something by 1, it's the same. Okay, cool. That's good. Let's go. All right, but now this one gets trickier. All right, and again, lots of things dating this package, this handout here. You're making $9 an hour working at McDonald's. How old is this? As old as me? No, there was no Facebook when I was in school. Oh, I'm so old. $9 an hour at McDonald's, which is like, I remember minimum wage being $9 an hour. Every year you work, after the first, you get a 4% raise. How much would you be making in your second year if you were getting a 4% raise? Figure it out. Use your calculators. I'm going to get my calculator ready because I'm going to show the people following along at home how we calculate it. What do you think?
Extra 36 cents.
Very good. How'd you get an extra 36 cents here?
I multiplied it by 0.04.
Ah, multiply by 0.04. And then you added that 36 cents on to 9, right? Hi, Val. You do? Okay, you're going to watch the rest of the video at home?
Yeah, I will.
Be sure to like and subscribe.
Of course.
Okay, great. Yeah, I'll see you later.
Yeah.
Yeah? Oh, cool. Bonus 10 points to Gryffindor. Deegan?
Oh, wait, when are we having our next test?
After this.
Tomorrow?
No, like right after I'm done this video. No, it'll be after next week. It'll be early in 2 weeks. I'll announce it at the beginning of next week, or I'm announcing it now. It's going to be like Tuesday-ish, but not this coming Tuesday, like a week Tuesday.
Next Tuesday?
Next Tuesday, yeah.
Next.
So not this upcoming.
Not the upcoming Tuesday after the long weekend.
Okay.
The week after that, yeah. Okay, so that's interesting. People like think about percentages as adding percents. So I want to just give you a new way to think about it. You multiply a percent in. Okay? You're always multiplying the percent in to grow things by percentages. So here is the way people did that. Okay, you took $9 and then you added $9 multiplied by 0.04. Okay? That's a cool way to do it, and it'll give you the correct increase, the wage increase of 36 cents. No problem. Let me give you a new way to do that. Or you can do it my way, which you're going to need to do if you want to use the functions well. You just take $9 and multiply by 1.04. And that's the whole answer. That's the only operation you need to do. Why are these two the same thing?
Because you're multiplying it by 1.
Because I add that extra 1.
So
What does the 1 represent in terms of percents?
The
Sydney?
original percent of $9.
Yeah, that's the original 100% of $9. And then we've added on an increase of 4% by multiplying once. Okay? Here's another way to do it. I take this expression and I factor out the $9. Okay? And then I will multiply that by 1 plus 0.04. You see how I just factored out those two 9s and it came in front of the brackets, and then I simplify inside the brackets? Okay, that's maybe you don't need that. But just add your 100% there and then do plus or minus your growth or decay. So on our next year, we're going to have 936. And then I go ahead and I get my calculator 9.36, and I multiply by another 1.04 to get the next year. Boom. 73 cents. Oh, I was expecting only 72 cents because I thought it was going to be 36 cents per year. But it turns out we get a 37 cent increase in the next year, whatever. I don't know, 9.73. Why didn't I write down that 4.4? In fractions of a cent. Yeah, be reasonable with your rounding. Round to the nearest cent at the very highest degree of accuracy. You probably round to the nearest like 10 cents, but whatever. No, people still get paid in pennies. Okay, 10, 12 you get in the next year, etc. Okay. So how are we arriving at the hourly wage each year? What is the thing we do to multiply by each time? 1.04, yeah, of course. Yeah. All right. So let's write them as a power, okay? Let's write them as like a series of things going down here. We take our initial wage, and we don't multiply it by anything there in that year 0. 0 copies of 1.04 we're multiplying by. And the next year, we have 9 times 1.04. In the year after that, you're just going to take the number that you had before, which was 9 times 1.04, and then multiply by another 1.04. And so on. After that point, I get a little bored of writing 1.04 so many times, so I'm going to write this as an exponent. This will be 1.04 to the what exponent? In this rung? Yeah, this one is power 3. And then 9 times 1.04 to the 4, and so on. So let's see if we can just punch that all the way for the fifth year. So we're going to do 9 times 1.04 raised to the 5. Whoops! That was a lot of 5s. That would be in the 5,555th year. Okay, we don't want that. Okay, so you're very nearly making $11 an hour after 5 years. So just stick with it, everyone. Work hard and good things will come to you. All right, 10.95. Okay, all right. Can you relate the hourly wage with the number of years you have worked in McDonald's to create an equation here? If we let y equal our wage and x equal the number of years worked, what's our function that relates y and x? Here's a little tip. You can write down this little grid. You say A equals initial value equals $9. B equals growth factor equals 1.04. That's growing by 4% each year. So then we just put those into a function. Okay? So my function will look like y is equal to the initial value multiplied by 1.04 raised to the power x. There's my y equals ab to the x. Any questions on how to use this idea? Identify from the word problem your initial value. That is your a value. Identify from the word problem your growth factor, not forgetting that 100%. Very common to use 0.04 here and say, why is my function not working? It just craters. It's like my wage goes down to 36 cents in the first year. Why? Okay? And then just feed them into this base function. There's your parent function. That works for like so many situations. Okay. So, how much would we be making if we worked at McDonald's for 20 years? How much money would that be? What you got, Jude?
Oh wait, it came up as
187.2
An hour?
per hour. So that's a one way to make lawyer money, everyone. Yeah. That's lawyer money.
That's solid.
Well, let's find out if that's right. That seems a little high to me. So here's what our function looks like, right? Y equals 9 multiplied by 1 point. I bet you maybe you have 1.4 instead of 1.04.
No, it's 1.04, but I times it to 20 instead of raising it to the power.
You multiply by 20.
Yeah.
Oh, that's interesting.
So,
Yeah, 9 times a little bigger than 20 is that, yeah. No, raise to the power 20, please. That will be different. Okay. So, this is how I punch it. 9 multiplied by 1.04 raised to the power 20. We're almost 20 bucks. Almost 20 bucks. So we're 1/9 the way towards your salary, very nearly. It's about a tenth. It's really close to a tenth of the salary you predicted. So we were only wrong by one order of magnitude. 19 bucks and was it 72 cents? Yeah, 72. Okay. Dun, 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 dun. There you go. That's how that one do. Okay? That's how that one do. All right. I'm going to pause the video. You're going to build your table here and think about how you're using this population growth of 6.5. But first of all, I mean, we are wanting to build a function where our x values measure, here it goes, we've got, where is it? Oh, I thought there was a thing. Anyway, what's our initial value of whales in this case? The population is going to grow by 6.5% each year. But what's the initial value? Yeah, there's our initial value. So what's our x value for the initial value? What value would you use for x there? 1993?
1 or 0.
I'd like 0. Yeah. So if we have our x value be 0 there, it would be 1 there, 2 there, 3 there, 4 there, 5. You see what we had to do? We had to create a kind of function that relates the year number to the x value we're going to use, right? 7, 8, 9, and 10, okay? And here's a little sentence that you might have in your working here. Let x represent the number of years since 1993. And just let that kind of sink in for a second. Why is that so important that we set that up that way? That we set x up as this like number that relates the year to the number of x, which is the number of years since that year. What would happen if we did this? Let's just find out what would happen if we said initial value equals 652. What's our growth factor here? How are we going to use this 6.5% to create a growth factor?
Would it be times 1.605? Or no?
Was it 1.065?
Which one is it?
0.65.
What is Katie talking about 1.065? Why does that make sense? So here's your 100% here, right? 1. And then here's where your 6.5% will go. If you had 1.65, that would be 65% growth. That would be just an incredibly explosive population growth. Yeah. Yeah. But if we had, So if we have 1.065, now we're growing by 6.5%. I saw this funny meme the other day where it's like the teacher says, "No one's crotch is that interesting. I know you're on your phone." So if I seem like I'm laughing, that's why I'm laughing. Okay. Anyway, so how can we build out your function, and we're going to compare the values we get for 2023 and compare our functions in just a moment. Go. All right. So we got this population of whales. It's pretty low. I mean, this whale population is in danger, but they're growing. So hey, good news. Let's find out. Rather than like filling in this whole table, using this idea to just create a function, and we're going to grow it, right? So this is like 652 times 1.065. Thanks very much, Katie. To the 0, because that's like the initial value, right? And then we're just going to crank that up and go down here and do 652 times 1.065 to the, let me check, 2003.
Wouldn't it be to the 10?
To the 10? Why would it be to the 10? It's the year 2003. 652 times 1.065 raised to the power 2003. Oops, that's one too many zeros. 2003. Oh, what? My calculator says only 3.9. Wait, it's 3 with 57 zeros after it.
Because you didn't do it to the 10, you had to do it to the 10.
Oh, so this if I like write this number down and I'm like, hooray, the whale population growing only 6.5% per year in 2,000 years would be like more whales than there is like grains of sand on the Earth. So exponential growth, when you have big exponents, exponential growth is not intuitive. It's shocking the numbers you will get. Yes, very good. This is incorrect. I'm just going to highlight that this here is incorrect. No. No. Okay? And we want 652 times 1.065 raised to the 10. Clear this nonsense. Hooray! We're about double. We've about doubled our whales in that amount of time, which is reasonable growth, okay? We got 1.224 whales. Sorry, no, we have 1,224 whales, sorry. Why don't I write down some decimal number of whales? Because then I have to think about what a decimal number of whales means. And if you've ever seen one explode on the beach, you know what I'm talking about.
Yeah, but you can have half a whale.
You could have half a whale like land on your car if that happened.
Could be a baby whale, could be a whale with no tail.
Yeah, this is the better way to think about it. It's a whale with no tail. Okay, is that there was like a whale in progress of being born. There was like 0.889. We were on the way to another whale, but we weren't quite there yet, right? So if you want to think about it in a kind of continuous whale arrival system, then that would be like the way to think about it. Maybe not a whale with no tail, because that's sad. That sounds like the children's book that I would write from prison. Like, it sounds depressing. Yeah. Okay. All right. So, develop an equation that will allow us to, okay, let's do it. What's our equation that will allow us to answer number 3? Someone who built the equation while we were on break. Jude, what you got?
652 times 1.065 to the x. And the x is the number of generations.
Yeah, where x equals the year minus 1993. Here's our function that relates the year number to values of x. You see how that little function is going to work? So now we can feed like years to this function and get it. So that's going to be 17, right? 652 times 1.065 to the 17. This is for year 2010. Clear. 652 times 1.065 to the 17. There we go. 1901.9. Okay, people want a challenge problem? So that would be 1902 whales, or thereabouts. You want a challenge problem? In what year will the population of whales be the closest to the year number? That'd be kind of fun. In other words, when will you have x equal 652 times 1.065 to the x? Challenge problem. Okay, let's keep going. Card depreciation. Oh, this was an exciting lesson. We were saving all the whales until now we have to depreciate all the cars. But I'm afraid unless you got some like fancy Camaro or something that appreciates, that gets more valuable every year that goes along. Usually cars go down in value as they get older. The same thing with like electric pianos or computers. Lots of things depreciate. So, most modern vehicles are losing 15 to 20% of their value per year. Okay? So, if we have this car, we buy it new for $42,000. After 1 year, how much will it be worth if it loses 20% of its value? It's not growing, it's shrinking. How do we do that? Yeah, what would you do? Because it's going to guide us to the way we're going to do it.
Could you do 42,000 divided by 100 times, or I guess you have to choose between 15 and 20, and then times whatever.
Yeah, we're going to do 20.
And then you just subtract whatever you get from that from 42,000.
Yeah, so we can do 42,000 multiplied by 20% to find out how much the value goes down, and then use subtraction. So we're going to, I'm going to write it up here. 42K, that's 42,000, minus 42K times 20%. Okay? So that's going to give it to us. If we use my factoring method from before, I factor out 42K, and that would be multiplied by 1 minus 0.20. That's 20%. So what do I multiply the value by to get a 20% reduction?
0.2, and then you take that number and minus it from the original.
That's true. That will work. But just like we did in the last time, rather than multiplying our wage by 0.04, and then adding it back into 100% of our wage, we can subtract the 20% from 100% of the value to get a single number that we can multiply by. What would that number be? How much of the truck's value remains, the car's value remains after 1 year if it's losing 20%? It had 100% of its value. It lost 20% of its value. How much is still there? 80%. So let's try both methods and see what happens on our calculators, okay? So I take 42,000, multiply by 0.2. This is how much it's losing, right? $8,400, okay? I'm going to just turn that negative and add it back into 42,000. Oops. There we go, 42,000. So we would have a new value of 33,600. Just going to write that down here. $33,600. That's kind of depressing because it's depreciation. Okay, let's try my way. 42,000 multiplied by 80%. That's just 0.8. I predict it's the same. It's the same. Cool, eh? So, this is the thing that we will review on Tuesday, and people who are here on Tuesday will be like, wow, I missed all that on Monday. I guess I didn't need to be there, because that's one simple idea. I take 100% and I add or subtract the growth or decay. In other words, in this one I do 1, which is 100%. If I multiply things by 1, I get 100% of them. Minus 0.2 equals 0.8. And that's our B value. That's our growth factor in these cases. That's the thing we multiply by each year to find the new value. It already includes that idea of multiply by 0.2 and subtract it from the original. Multiply by 0.2 and subtract it from the original. But that's two operations. Building that function, I'd have to have those operations nested within one another, and I can't use exponents to show you that function. With 0.8, I can. Just multiply by 0.8 that many times. Or use an exponent. And that's how that goes. So the equation that relates the value of the car to the year. This one we don't have to do any fancy x conversions because we started at year 0. I've owned the car for 0 years, it's worth the sticker price. I've owned the car for 1 year, I multiply by depreciation once. Okay? So what's our equation look like down here? What's my A, initial value?
The 42,000.
Good. And the B, growth factor?
0.8.
Yeah. And here you might put a growth in cheeky quotations because we know that 0.8 is not in fact growth, but decay. So we have exponential growth. Things grow and people are happy unless it's COVID cases. Exponential decay. Things decrease very quickly. Another thing that would decrease very quickly would be, say, the temperature of this coffee. started out close to, that was pretty cool when I got it actually. Say it was close to 100 degrees Celsius, extremely hot coffee. And then it would cool down quicker in the beginning, and right now it's basically the temperature of the room. It decays exponentially. This shows up in so many situations, not just cars and generations of dogs. Okay, so our function looks like what? Y equals, where Y is the value of the car, and X equals the number of years. There's our let statements. What's our function look like?
Would it be, y equals 42,000 times 0.8 to the power of x?
So we have $42,000 multiplied by 0.8 to the power x. Beautiful. That's great. And they'll be frequently written like this. Initial value, brackets around your growth factor, raise the brackets to the power x. Okay? That's great. So there's our function. And we can use that to predict future values. Okay? So these will create, let's take a look at that in Desmos actually, since we've got a little bit of time and we've got some dedicated students that are a little bit ahead with these ideas. It's great. So we're going to type this in. Y equals $42,000 raised to the power 0.8 and the bracket to the power x. I don't see anything, Mr. Jennings. Why don't we see our function? So I go in here to graph settings. Here is not the right way to find your function. I'm just going to zoom out until I find it. There it is. Is that really showing me this function? Like, am I really seeing what it looks like? Not really. I'm also looking at 150 years there. Am I going to own this? Is this function really going to, is that a reasonable domain for this function? How much am I going to be able to sell this Ford Mustang in 150 years? I'm not interested in that domain. So I go in here to the wrench and I adjust my x-axis and my y-axis appropriately. What would be a good number to see for y values?
10, 15.
10, 15? Oh, for x values?
Oh, maybe, yeah.
Yeah, let's talk about x values first. What I don't need to see 136 2 years ago. I probably just need to see, like, let's just put a -1 so we can see the axis there. Okay? But you said we should look at like 15 years or something like that. There's 9 years. Let's do 20 years. There's 20 years. Now, what values of the car are we interested in?
Tallest would be 42,000 and lowest would be 0.
Yeah. Yeah. So let's look at, I'm just going to put 45,000 here. There. Look how beautiful our function is. I'm in the way of it. There we go. All right. Okay. And look at what we see, everybody. So here is the initial value of the car. Great. And then we could, if we want to do things like y equals 10. Sorry, not y equals 10. X equals 10. To say, what's going to be the value at 10 years? Oh, there it is there. $4,500. $4,510 thereabouts. Okay? So after 10 years, it's worth like a tenth its value, having lost 20% of its value for 10 years. Okay? We notice that it's a curve, and it never quite gets to 0. It will never get to exactly $0. This is already nonsense over here at 30 years. It says the car will only be worth $50. Does that make any sense? I'd buy a 30-year-old car for $50 because I can sell it as steel for more money than that. So there would be a kind of floor to this type of function that would kind of limit your range. It would never drop below its cost as like raw materials. Okay? But for the most part, this function is going to be a pretty good predictor. And then I can use even these types of sliders to say, well, what about at 4 years? And then just find that value there. And that's kind of visually how we read the graphs too. So Desmos is your friend, everybody. Desmos is your good old friend. You got the app on your phone. That's why you're all looking at your phones right now. And by you all, I just mean like 2 or 3 of you. Okay. And then here's a metaphor for like how much attention people are paying to me. As the minutes go on in class, oh, it decays exponentially, and then I end up in the bottom corner. All right, let's go. Okay. So, what was different about this from previous examples?
It was the only one that went down.
Yeah, yeah. So we want to be good at both situations. Exponential growth, exponential decay. Both are like things that we need to understand in order to work on this topic in finance, because money is exponential, interest rates and all of that. In terms of biology, how many bacteria are there in the petri dish? How much of the drug is left in the patient's body after a certain amount of time? Many of these are going to follow exponential models. Okay? And things are going to both grow and decay. So we need to have both of these skills. All right, very cool. Okay, and then, so then we've got Detroit. And there's not really that much that's new down here in Detroit. So go ahead and try that example on your own. And yes, thanks everyone for showing up for your math learning. Any questions? Hit me up in the D2L. Yeah, Jude.
Okay.